So the language of identity and inverse is a language that we've been using in the context of functions and composition. So in order to understand the intentions behind the terminology, it's good to remind ourselves how that language was used in a context of basic things that we're used to. So 0 has the property that when you add it to a thing, you get the same thing. 1 has the property that when you multiply it by a thing, you get the same thing. These properties are called, these features of 0 and 1 make them what we call identities. So 0 is an identity for the operation of addition. It's an identity for plus, and 1 is an identity for times, for multiplication of numbers. And in a similar vein, if you take id sub something, where you have to put the appropriate thing, and you compose it with a thing, where by thing you have to put in the right type of thing, right? Like here it was a number, here it was a number. What type of number? I'm kind of being vague. Here thing is going to be some kind of function. And the idea is that you get the same thing. Right, this is the content of Theorem 65, parts 3 and 4. It's saying if you take a thing composed with id of the appropriate type, then you get the same thing. And you need to say it separately about both directions in which you can compose id. So there's these two sort of separate statements, where if you choose the right id here, then you get the same thing. There are a couple of ways in which it's more subtle and involved than just what's going on up here. One subtlety is this order mattering. So these are two separate facts, where up here, if I just wrote like thing times 1 versus 1 times thing being the same thing, those are not two separate facts because multiplication is commutative. Composition is not, so I need to think of these separately. And another subtlety is, depending on the kind of mapping you put here, you need to choose the right kind of identity, right? And depending on the kind of mapping here, you choose the right kind of identity. But anyway, this is why we call id sub the appropriate thing an identity in some sense. Now, what about the language of inverse? So remember that 0 was an additive identity and 1 was a multiplicative identity. Now, if I take a thing and I try to add something in order to get 0, in order to get the so-called additive identity, or if I take a thing and I try to multiply by something in order to get the multiplicative identity, then that something that fits there, if there is one, is referred to as the inverse. So what would you put here? You would put negative of the thing, right? And so we call negatives additive inverses. So the negative of a thing is the additive inverse of that thing. What would you put here? You would put the reciprocal, right? So a reciprocal of a thing is going to be the multiplicative inverse of that thing. It's that which, when operated with the original thing, gives you the identity object. Then in the context of functions and function composition, if what fits on the right-hand side as the identity object is going to be the identity function, like maybe id a on subset a, and the operation here is going to be composition, then we are interested in figuring out what could go here and what could go here in different contexts when there is something that goes there. There's not always something, right? Even up here it always works, but up here, if your thing is 0, then there's no way to find anything to multiply and get 1, right? If the original thing is 0. So it's not always possible to invert everything. 0 has no reciprocal. So when I put this blob here, I'm not trying to refer to what fits there. I'm trying to refer to what fits there in the event that something does fit there. But it might be that nothing fits there. Anyway, if something does fit here, then we call it the inverse of f. Okay, but we already have a language for, we already have a definition of the word inverse, right? If I can find it. Oh, it's down here. Yeah, if you have a function, then if when you flip it around, when you take the reverse, that's also a function, then we refer to that as the inverse of f. And that's pretty common usage of the terminology. But the intention, the reason that's a good terminology is because we will find, in a moment, we will find that when f has an inverse, in the sense that f reverse is a function, then we end up in this nice situation. But it's a little bit more subtle. So we have to worry about what kind of function, what kind of set to put here, and we have to worry about which orders work. Sometimes it can be that there's something that fits here and makes this true, but there's nothing that fits here, and this is more like dividing by 0 or something like that. In those situations, you might say f is right invertible but not left invertible. So things can get a little more interesting. All right, so here's one theorem about invertibility of a function leading to a situation which you might call algebraic invertibility. This is kind of an algebra discussion here. So assume f maps x to y, and f is injective. Remember, injective, we found, is equivalent, from theorem 72, is equivalent to just saying f reverse is a function. So it's equivalent to saying f is invertible. So assume you have an f and f is invertible according to our original definition of invertible. Then the conclusion, or the goal of what we're trying to prove here, is going to be one of the two directions that are showing up here. Which direction? F. This one, actually. That f is invertible in this sense. So then our goal is to prove this, right? Our goal is to prove a certain equality. But this is an equality between functions, right? So while I could take the double inclusion route, that would be probably wasteful. I can use previous work and write a much more natural looking proof by using the tool that we established specifically for equality of functions. So this is going to keep coming back every time we wanted to prove two functions are equal. Two functions are equal, as long as you know they're functions, then they're equal if and only if the domains match and the outputs match for all inputs. So to use this theorem, we need to know that we are looking at two functions. And then when we use this theorem, we have two things left to check: that our two functions have the same domain and that their outputs always match. So are we looking at two functions? These are the two functions these are the two objects we're trying to show are equal. Are these objects functions? So id_x is a function by, let's see, it must be one of the basic facts about identity. Yeah, right there, by 1, right? This mapping statement says three things, and one of those three things is that it's a function. Let me just write sentences and then in parentheses just write the reason. Sometimes I like to do that. Now, I want to argue that this composition here is a function. So this is all in order to show that I can apply theorem 53 here, which requires that I be looking at two functions in order to use this to show that they're equal. So I want to know that this composition is a function. Probably essence of composition will help, right? So let's go to essence of composition. And it says, okay, if I have two functions, then their composite is a function. That's pretty good. Do I have two functions? I have f. F is a function by assumption. F reverse, is that a function? Well, f is injective. And let's see, does that make f reverse a function? Yes, according to theorem 72. If f is a function, then f reverse being a function is equivalent to f being injective. So this is an if and only if here. So f reverse is a function. That's theorem 72. So this is a function. And now I'm using theorem 63.1. Okay, great. So I have got that the two things that I'm trying to show are equal are functions. This is a function, and this is a function. Now, do their domains match? So the domain of id x, well, that's x, right? By some theorem, probably the basic facts about identity. Yep, it's contained in this mapping statement. The domain of id a is a. And what about the domain of this composition? So one way to get at the domain of a composition is to use theorem 62. Alternatively, I could use theorem 63 part 2. Personally, I like to use theorem 63 part 2. I just prefer it. Okay, so I need to establish two mapping statements, and then it gives me a third mapping statement for the composition. So I need a mapping statement regarding f, and I've got that. F maps x to y. So since f maps x to... But am I going to get a mapping statement for f inverse that starts with y? Will I get f inverse maps y to something? Not necessarily. I actually don't know that f is bijective, right? That's what we discussed in the previous video. Only when f is bijective can I be guaranteed that the inverse of f has a y here. So what do I know about f inverse in terms of a mapping statement then? I know that it maps whatever is the range of f, which might be smaller than y, to x. So that would be theorem 73 here. That was the presentation problem. So this is what I know. Okay, so it looks like I cannot use that essence of composition result on these pair of mapping statements, right? F goes x to y, and then f inverse does not go from y, it goes from range f. But maybe I can replace this mapping statement by another one. F goes from x to range f. That sounds plausible, right? So let's establish f goes from x to the range of f. Since f is a function, that's part of our assumption here. Well, let me just go ahead and say it, and then I'll talk through the justification. I think we can just say this to start with. We have f maps x to the range of f. So this says three things. F is a function. We knew that from here. The domain of f is x. We knew that from here. The range of f is a subset of what I wrote here. But what I wrote here is the range of f, right? So the range of f is a subset of the range of f, of course. So if I want to give a parenthetical justification here, this is since f maps x to y, and range f is a subset of range f. Although it looks silly to even say that. Okay, now let me pull in the other mapping statement. That was by theorem 73, which applies to any injective function from x to y, which is what I have, right? This maps the range of f to x. And now I can apply that essence of composition theorem. So that's this one, part 2, 63.2. Okay. By theorem 63.2, f inverse composed with f maps. Okay, so here's the way I figure out how to apply it. this composition, you sort of read it from right to left, right? So this composition says do F, then do F inverse. So I'll start with F. Where does F start me? It starts me in the set X. So I go X here. Then I go to range F, which is the domain of F inverse. Then I do F inverse, and that ends me back up at X. Okay, great. So now I know about, the whole point of this was to know that the domains of these two functions match, and they do. So in particular, from here, we know that the domain of F inverse composed with F is X. So from here and from here, the domains match. Okay, now maybe it's time to start a new paragraph. Since we showed one of the two things we have to show, the domains match. Second thing that we should show, I guess, is that they give the same output on any given input. So consider anything in the domain of either of them. Either way, it's X. X is the domain, so let me just use X. So new paragraph. Consider any, and I like to use lowercase letters for things that are in capital letter named sets. So consider any little x and big X. Now my goal, so let me just put that in green. This is kind of part of my scratch work. My goal is to prove that this thing of X equals id of X. This is a capital X in the subscript. So that's the goal. So let me write down the basic argument and then go ahead and justify each step of it. So when you apply a composition to something that you can apply the composition to, we know from essence of composition how that operates. It gives me first do F, right? And then to the result of that, apply F inverse. That's what it does. And if I understood how inverse works, if I properly understood that, F inverse should send an output back to the input that it came from, right? This is what we were saying when we discussed theorem 74 here. We were saying the inverse of a function, when it makes sense to apply it to something, sends an output back to the input that it came from. So if I'm understanding that correctly, that should let me get X here, right? F of X is the output that came from the input X, and then F inverse applied to that sends it back to the input that F of X came from, which was X. Okay, that doesn't sound so fully justified, but we can work on it in a moment. And then my goal is to show that this is the same as id X of X, but id X is the do-nothing function, right? So that should be the same. So this is the argument, but each line needs some justification. Is there anything that can immediately be justified? If there is, then I'm going to just write the justification to the right of it. This is a nice way to arrange things when you're writing your homework. If you have a chain of equalities showing up, then you can display it like this. And I'll show you how to do this in LaTeX after the proof. And then you can, if you want, you can put some words here that justify each individual part. That's if a small phrase is sufficient to justify that equality. Some of them will need a little bit more. Okay, so what justifies from here to here? That's definitely essence of composition, right? So back to essence of composition. Over here, theorem 63, part 1, that's what tells us that this is how composition operates. So I think the justification will be theorem 63.1, but hang on. There are hypotheses in that theorem. So I need to check that everything works. So this requires that the two things here that are getting composed are functions. Okay, we've already discussed that f and f reverse are functions. That was discussed above, so that's good. And then this applies for any x in the domain of the composite. So we had better be looking at an x in the domain of the composite. But the domain of the composite is capital X, and little x is in there. So this theorem applies. No problem there. Now, since that's sort of like, since the checking the hypotheses just amounted to looking at things that we already previously stated, I'm not going to write any more about that. So you can sort of leave it to the reader to verify that the theorem does apply according to what we've done. But if checking that those hypotheses works, that those hypotheses hold, if checking that actually required proving something further that we didn't already say, then you should definitely prove those things. Okay, what about from here to here? So we suspected that from here to here would use theorem 74 here. Does it? So if it can use theorem 74, then it must be using theorem 74 with the role of x being played by, with the role of y. So I'm just looking here, I see f inverse of f of x. So maybe the role of y is played by f of x. Now, if I have x in the domain of f, so, how to put this? So when I apply this, the role of y in my application of this is going to be played by f of x. So to check that it works, I need to know that f, the role of f is being played by f. I need to know that f is an invertible function, which I do. We checked that above. And that little x is in its domain. Yes, x is the domain of little f. And f of x, which is what's playing the role of y, is in the range. Yes, f of x is in the range of f. I think that fact, that f of x is in the range of f, that we kind of get without saying much. I think because of theorem 52. So if you have a function, then something is in the range of the function if and only if it's f of something. This is an if and only if. When you take f of something in the domain, then you get something in the range. Okay, back here. So then what does this tell me? Now I know I can apply it. It tells me x equals f inverse of f of x if and only if f of x equals f of x, right? So basically, just if you're having trouble following this, just take a piece of paper and write down what this is saying, but replace all the y's by the symbols f of x. And you'll see here it says f of x equals f of x, and here it says exactly what we want here. So this did work due to theorem 74. And then finally this one. This is going to be one of our basic facts about the identity function. 65.2. That the identity function is the do-nothing function. And this works whenever you take something in the domain, of course, and little x is in the domain, big X. So then we are done, because we have shown the two things that need to be shown according to the equality of functions theorem. So by theorem 53, since we have shown that the domains match and the outputs match for any given input, we are done. All right, so then when you have an injective function, it's left invertible. This is a way you can phrase this there. When you have an injective function, it's left invertible. There's something you can multiply or compose on the left in order to get the identity. Now, what happens if you compose in the other direction, just out of curiosity? So right now what we're looking at is this situation, F injective, and then we're doing what we looked at here is F inverse compose F, right? So if you write that out kind of in this notation, F goes from X to Y. F inverse goes not from Y, but from range F to X. Then what we did is we sort of replaced this codomain by a smaller codomain, and then we went from X to range F to X, right? So I sort of removed this and I said, think about the codomain of F as being the range of F. And we argued just now that this is the same as the identity. What about composing the other way? So what would this be? Well, let's see. So this says do F inverse first. That starts at range F, actually, right? And then it lands you at X. And then F is X to Y. And if you want, you can write range F here, right? You can write down this smaller codomain, the actual range of F. Then, this is the inverse, then you should be able to prove that in this situation, this composition, if you go from here to here, will be the identity, but on the range of F, right? So you should get F composed with F inverse is the identity on the range of F, which is kind of an ugly result, right? It would have been nice to get identity on, not the range of F, but identity on Y. Since this is the identity on X, it would have been nice if when you did it the other way around, you got the identity on Y. But nope, it can shrink like that. But what if F is a bijection? So instead of an injection, let's suppose it's a bijection. So I'm just adding in that it's also surjective onto Y. Then the range of F is Y, right? And then we don't have this trouble. Like, I can put Y here. This is Y. This is the identity on Y. So then this just becomes identity on Y. By the way, I'm not saying that we proved this here. This is something that one has to prove. I'm just discussing that you could write a proof along the same strategies used up here. Yeah, so if F is a bijection, then things are very nice. So what we just proved in the majority of this video was Theorem 76, and what I'm discussing now is Theorem 77. Theorem 76 was about when you have an injection, and then you have this one-way good result. But when you have a bijection, then you have good results both ways. And a way that I like to interpret what these are saying is, I like to think of F as doing something and F reverse or F inverse as undoing whatever the thing is that F does. And remember, identity does nothing. So this is like saying undo what F does, and then, so remember you read compositions right to left, undo what F does, and then do what F does. That's the same as doing nothing. And this one is saying do what F does, then undo it. That's the same as doing nothing. Okay, so I will not go over the proof of this one in the lecture, but I hope you will study it in your reading. As for this one, Theorem 78, that one is going to be your homework problem for this time. And it's 5 parts, so it's 5 separate proofs, but each of them is not that long. It might just take you a while to figure out the trick on scratch paper or whatever, but once you figure out what to write, it shouldn't end up being too much writing for each individual one. I just wanted to give some advice. So you've got this you've got some global assumptions for the entire thing. F maps x to y and g maps y to z. And then it allows you to make some deductions about who's injective and who's surjective and who's bijective as you compose. So part 1, composition of injectives is injective. Part 2 is kind of interesting. When a composite is injective, then you know that the first thing, the thing on the right, is injective. And then part 4, you get a similar kind of thing for surjective, but focusing on the thing on the left. So I really like this theorem. I think it's the first truly fun theorem in this whole section, probably. So that's part of why I'm saving it for homework rather than doing it here. And my advice is when you prove certain parts, feel free to use previous parts that you already proved. So as you prove part 5, for example, part 5 should be pretty easy because it's about bijective, and you already have results about injective and surjective from above. So allow your proofs to be shortened by the fact that you're allowed to use previous parts. And one last bit of advice, when you're working with using or proving that functions are injective or surjective, here's what I recommend. For injectivity, use the definition rather than using this. This is useful sometimes, and you can use it if you really feel better about using this, but I would recommend using the definition. So like if you want to prove a function is injective, then you're proving that for all xy, fx equals xy implies x equals y. So then to prove a function is injective, consider any xy in the domain, and then assume fx equals fy, and then your goal becomes to prove x equals y. That's kind of the approach. On the other hand, for working with surjectivity, sometimes this is more helpful, and you can use this if you want, but I think more often what is more helpful is the characterization of surjectivity in Theorem 59. So say I want to prove that my function mapping x to y is surjective onto y. Then what I would do is consider any little y in y in order to prove this for all, and then my goal becomes to find some x in the domain such that f of x is y. So basically consider any potential output, and then show that there is an input that makes that potential output actually be an output for that input, if that makes sense.